And so this one is, this is actually a little bit more complex. So I think it's a nice example to go over. And this is what's called constructing optimal BSTs, and this is a binary search tree. Okay, so let me give an explanation of this. So suppose there is a universe sigma. So, just for simplicity, just think of this as 1 to n. And we need to search for these elements. So every time, so you could think of maybe like each element is a user of a website, and there is, some object storing user data. When the user logs in, we have to fetch the data. Right? So what is the data structure to solve this problem? Yeah, any guesses, thoughts? This is your problem. I mean, I guess it's already written. It's already written. What you would do is a BST. You could build a binary search tree on the keys sigma. Okay. So now suppose there are m lookups to the table. What is the total runtime? Right, so you have n, the universe size is n. There are m lookups to this table. I shouldn't say the table, to the binary search tree, I'm sorry. What is the total runtime? Fairly basic algorithms question. Okay, so maybe I should actually give examples. Is it going to be O of m? Is it going to be O of m log n? So n. Okay. Relaunch the poll. Okay. Okay. Okay, so yes, most of you remember your basic algorithms knowledge. It is m log n. And so we know that this is the best you can do in general. But suppose some keys are more frequent than others. So this is actually an important problem. So think of it as, let's say you know that there are some users who tend to log in a lot more frequently than others. And this often happens. There are some users who use the website very often. Some users only log in like once a month. And some of them, maybe they only log in once a year. And so somehow it feels like you should be able to do better because you should search more quickly for the few users who are frequent and spend more time on the users who are less frequent. Like in this case, pretty much any user will take login. So some keys are more frequent than others. And the question is, can we improve the lookup or the search time? Okay, so let me now make this formal. I'll say, suppose we know or we have what I will call a frequency function. So what I mean is we have some function. This is just saying that for each little sigma in sigma is the number of lookups. Like suppose you already know this, and maybe you find this from past data. For every character, that's like every user, you know how many times they're going to log in, maybe over a month. Like based on past data, you have a pretty good estimate of this. Okay, so that's the number of lookups. Now in a binary search tree, each character, each has a depth, right? So if you think of your binary search tree as, maybe over here you have 50, you have 42, you have 101, 90, 78, so on and so forth. The depth of a character, which is the same as the node of the tree, is the number of nodes on a root to node path, meaning that the depth of this is going to be 3, the depth of this is 2, the depth is 1, 2, 3, so on and so forth. So each character has a depth because you've put it in a binary search tree. And so the depth of sigma is the depth of a character. So think of these two functions that you have. One is the frequency, which just tells you how many times you're going to look up a character. And then if you build a binary search tree, for each character, you have a depth. Question: what is the total lookup or search time? Is it the summation? Okay, so sigma is unfortunately overloaded here because sigma looks like that. Is also for sum. So, all right, my apologies. I'm just going to call the universe gamma, just so that, okay, and I'll say this is gamma. Is it going to be F gamma, D gamma? Is it going to be the sum over all of these of F of gamma plus D of gamma? Or is it going to be the sum over all gamma of, f of gamma log d of gamma. Okay, this is the last question for the day. What is the answer? Okay, so it seems like there's a fair bit of confusion on this, and maybe this question is a little challenging to think about. So instead of telling you the answer, I'm just going to tell you what the logic is, and then when we come back in the next lecture, we'll actually discuss the answer. So look at a character sigma. Gamma. This is the number of times you search for the character. For every search of the character, well, I guess I'm just going to tell you the answer. Every search of the character, how long does it take to find something at a depth of d? It takes d steps. Right? So if you look at some character down here, how long is the search going to take? It's going to take the depth. And how many times did you search for this? Well, f of sigma times. So actually the total search time is f sigma times d sigma, and the problem is to find the BST that minimizes this total lookup time. Okay, and this is a classic dynamic programming example. So I think I'll end now. So in the next lecture, we will go ahead and we'll discuss the dynamic programming solution for this question. So I'll end the lecture now. I'll still stay on for a few minutes in case any of you have any questions to ask me. Right? And I will see you in person, or at least some of you in person, on Thursday.